All right, so let's finish up this chapter. We're gonna look at, so the last force we're gonna look at is tension. And so, when you, especially when you're looking at free body diagrams, tension you can represent with, I mean, you can just draw the free body diagram, put the tension vectors on there. There's a couple of ways you can look at the free body diagram. And then we're going to talk about, you know, how you analyze angles from that and how you analyze the tension vectors. So what do you think? Well, I mean, it says there, but I mean, you ever played tug of war? The force going back and forth on the right and the middle, that's tension. However, one of the things you have to get used to with tension is within a single cable, it pulls both ways. So it just depends on how you're looking at it. So if I have something hanging from the ceiling, the object itself has its gravitational force, and then the tension in the cable is holding it up. So the tension is going that way according to the object. However, the tension according to the ceiling is going down. And it's the exact same tension. So you have to think about what you're looking at. So let's look at a couple of cases for this. And some of these you're going to get into. Your high school teachers would have shown, for example, solving a system of, let's say, 3 equations and 3 unknowns. You ever done that?
Yeah.
So a system of linear equations. So tension is going to kind of require you to think through that. You're going to solve for one, plug it into another, and so on and so forth. So like, let's look at the easiest case, case 1. So I'm going to draw a little. See, and then we're going to have cable. I don't know, suspending some kind of mass. Then we have to think about this. So first off, you're going to have your gravitational force of this object. Well, gravitational force, it's also your weight. What else does gravitational force equal now that you've looked at gravity, mass times gravity? So that's gonna, so this is a good start like to get into your mind what's gonna happen in the next chapter. Your mass times gravity, that's a mass times an acceleration. And what is mass times acceleration? And that's what law? Newton's second law. So your next chapter is really going to be all about motion and Newton's second law, which is F equals ma. But what else you have on here? Is you have a tension in the cable holding the object up. So again, when you're drawing free body diagrams for this stuff, you could just take the object, put it in there, draw the tension vector, the gravitational vector, and that would be your full free body diagram. You don't necessarily have to draw the ceiling that it's hanging from. But let's look at how we would solve for tension in this case. Well, so we have the sum of our forces in the y direction. It's going to be our tension vector. Our mass times gravity vector. What does this all equal?
0.
0. Why? Nothing's moving. This system is in equilibrium. So we think about which way things are pointed. So what I usually do, I'm just going to mark my positive y direction. And then I'm going to say, well, that means that tension, you're going to get the magnitude of the tension in the positive j hat direction. you're going to get the mass times the gravity in the negative j hat direction equals 0. When everything is in the same direction, you can remove the unit vectors. So in this case, your tension is going to equal your weight, your mass times your gravity. Now at this point, we're at a magnitude, but at the same time, your tension, points in the positive y direction for the object. And so you could represent it as a vector with your positive j hat on there. Or if you're more comfortable with x hat and y hat, by all means. Okay. Let's look at case 2. Okay. I'm going to try to get this centered. It's pretty centered. It'll work. And then what I'm going to have two cables. I'm just going to pretend like that works. Okay, now I'm going to divide this down the center because both of these hang at the same angle. Now you'll notice, eventually you might have to prove this, but you'll notice if you have two tensions at the same angle, they're going to be identical. So let's think about what we have here. Okay, well, I have the tension on the wires. My gravitational force. Now let's think about how we start analyzing this. So if you were going to draw a free body diagram for this, you could say, well, let's just go ahead and move our object out here. Okay. Center of mass. Mass times gravity is going to go like that. And then with your tensions, you can draw them in like that. And you either start analyzing from here, because you could say, well, I can put an X direction in there, or a Y direction, and I can put my X direction that way. And you can start analyzing them. With your X all the way across, so we can analyze both vectors. So then we have to start thinking about what we need to analyze. We can put our angles in. And then we can say, well, so each one of these tension vectors is going to have an X and a Y. We have to analyze, we have to then find the components of each one of those because of course they're moving, they're directed in 2 dimensions. So let's start looking at that. Well, each of my X components for tension, they're opposite my angle theta, which makes the trig function what? Sine. So opposite the angle is a sine function. So then I could analyze my y direction, but I know it has to be, oh, hang on. Forgot something, didn't I? Yep, I need the magnitude of the tension. There we go. Now, my y direction has to be the opposite one, but if you analyze it, you'll notice that your y component is going to be adjacent to each theta, so it has to be cosine. So let's start looking at our sum of forces in x and sum of forces in y. Now, what do you think is going to happen in the x direction? Yeah, they're not going to have anything to do with this. And so that's going to be one of them, positive I hat. The other one is negative I hat. So your x components all end up being zero. Do you remember? So this is what I was talking about. Who remembers in chemistry when I talked about polarity vectors? And the polarity vectors go in 3 dimensions. And sometimes they cancel out because, well, if you remember for example, your trigonal bipyramidal structure. I'm guessing most of you don't remember that. Your components around the center, since your center there is a circle, all of those vector components around there end up canceling each other out. But you can still, I guess you could still end up with polarity. It depends on your top and your bottom. But still, polarity is really an analysis of vector addition. Where do they cancel out? Where do they don't? That's why, for example, carbon dioxide is nonpolar. You have the exact same polarity vector, one going that way, one going that way. Now let's look at the analysis in the y direction. Okay. So what are all the forces we have going on here? Well, I have a Ty. That's a Ty. G, that is all going to equal 0. Now I have to ask myself what direction they're going in. Now, when you're going through your homework, you would start here with your theorem. Now, I'm putting in the I hats and the J hats because I'm showing you that some of the vectors go in positive I hat direction, some go in negative I hat direction, so on and so forth. You don't have to put that step in. What you would do from here is you could skip the I hat J hat step. You could say, well, I have a positive Ty, those are both in positive J hat. And what's the sign on Mg going to be? What J hat direction is that in? Negative. So you can skip straight to this step if it makes sense to you. I was showing you the extra step to show you that the positive and negative that will go on each one of these is due to the direction of the vector. So then what you're going to have, 2Ty equals Mg. Let's go ahead and put in Ty. That's 2T cosine of theta Mg. And then what we can do is if we solve for T, we would end up with mass times gravity over 2 cosine of theta. Now, if you were working through this in a problem, the x components, even though they cancel out to 0, I would still expect you to show that. Don't just tell me they become 0, because I'm going to ask you, how do you know that? Okay. Case 3. gonna have support there, draw on our mass. Okay, and then no support there. So what we're looking at, this is going to be your most general case. Then we can say we have a cable supporting there, supporting there. And they're both supporting at different angles. Now, of course, you know that you're going to have a tension that way, that way. These cannot be the same tension. All right, so let's think about a free body diagram for this. Okay, so the first vector that goes on here is the easiest one. It's our mass times gravity vector. Whenever I write that gravitational force vector, why do I only put the arrow on top of the gravity?
Mass is a scalar.
Mass is always a scalar. Gravity, your acceleration due to gravity is your vector. And then otherwise, we're going to have one tension going that way. Going off that way. Let's figure out how we can analyze this. So y over positive x okay, and then of course in here we have our angle phi over here. We're gonna have theta, and then we can start looking at our components. So let's see. Then so we're going to have T2x, T2y, 1x, 1y. Then we have to start analyzing all these various components because we're going to end up needing to solve for tension 1 and tension 2. And you're going to see this better fleshed out in an actual example, but I want to show you that you may have to solve for multiple variables, and you're going to have to use the equations that are available to you to be able to do that. Okay, so let's just start with, okay, so our x's are going to get which trig function? Sine, because they're opposite their angles. So then the y components are going to get the cosine function. So let's look and we say x is t1 sine of phi, y, t1 cosine of phi. T2x is T2, sine of theta. T2y is T2, cosine of theta. So now we have our vector components, and we can start putting things together. Okay, well, let's look at the sum of our forces in the x direction. Now, if we take a look, the only x components we have are T1x and T2x. Okay, so those are the only ones we're worried about right now. So that means we're going to get negative T1x minus T2x 0, which means we're going to end up with T2x equals T1x. And now let's substitute in our components. So this one is going to be T2 sine of phi, T1 sine of theta. Now, as for right now, there's not much we can do with this because we might know theta and phi, but we don't know T1 and T2. We need another equation because we have two unknowns. Where do you think our other equation is going to come from? The y direction. So let's look at that.
Wait, will you go back up real quick?
Yeah, you're writing really fast.
By the time this year is over, I fully expect all of you to be having mathematics nightmares.
Thank you so much.
Hey, I do try to go through every step because when I was where you were at, I had a professor put a differential equation up on the board and go, and then here's the solution for it. And I said, how do you know that that's the solution? He goes, well, when you've been doing this long enough, you know what the answer is. I'm like, I've been doing this for 3 days. Can you help me out here? Okay, so what are our y forces? Well, we know we're going to have T1y, T2y. What else? G. Okay, now, which ones of these are positive j hat? Which ones are negative j hat? Only the mg is the negative j hat. So we can say that's going to give us T1y plus T2y minus mg equals 0. Okay, well, we can mg. Let's go ahead and put in our components. And now we end up at a place where we have 2 equations for 2 unknowns. So you can solve this as a linear system. You can solve for one of the tensions and plug that in. So like, for example, and don't worry, I'll come back down in a second. If I go back up here, and let's say I solve for T2. T2 is going to be T1 multiplied by the sine of theta over the sine of phi. Now, I have an expression for T2 that I can put into my second equation. So that entire equation will only be based on trig functions in T1, well, mass times gravity, which you usually have that as this mass weighs 240 newtons. So your mg would just be your 240 newtons. And so you're going to come back down here and you say, well, that means I can do T1 phi. I'm going to plug in that T2, which is going to be T1 sine of theta, sine of phi, cosine of theta equals mg, which now we have a function where you would have, in your problem, you would have theta, you would have phi, you would have your gravitational force. So you have all of the numbers now except for T1. So where could you end up with this? You could say, well, because in your homework, you'd have to solve for T1 before you started putting numbers in. So let's go ahead and multiply through by that sine of phi.
Why do you put T1 in?
Why'd you put T1 in front of where you sub T2 in?
Because up here, we solved for T2. And I put this in the place of T2. Once I have an expression for the second tension, I can put that in where that variable's at. So if you take this, you're going to sub it in where you see T2. Everything else stays the same. So that means this whole thing right here, T2. Now I looked for some trig identities. None of them were nice. This is about as nice as this equation gets. We could factor out the T1.
Why didn't you multiply NP by sine?
Oh, because I'm supposed to. MG. There we go. That way the sine of phi multiplies all the way through. And then if you were solving for T1, so all of that mess goes in the denominator. And now from here, what you would have is you have a representation for T1 that you could plug all the numbers into that you would have going into this, such as your theta, your phi, because really all this is some hefty calculator work, and then plugging in the angles where you see where they're needed, and your mg would just be your gravitational force. So again, imagine a problem where you say the weight of the object is 560 newtons. Well, for example, your 560 newtons would go in the place of m times g, and then you start plugging in all your angles, and then do some calculator practice. Now, this is not the class where we do things like Tim Keith and I take your calculator away from you and make you do this in your head. That would be awful. But this is an example. So this is your most generalized example of your tension. And what you're noticing here is you're getting in. So you might want to do some review on solving linear systems, because that's what we had here. We had a system of two unknowns, T1 and T2, and two equations. Now question, can I solve two unknowns with one equation? Can I solve three unknowns with two equations? No, you have to have the same amount of equations as your unknowns. You can have more, which can just make the situation easier, but you have, if you have three unknowns, you have to at least have three equations or you can't solve the system. Now, I think for this year, we'll just leave it to solving and substituting, because you can actually turn a system of linear equations into a matrix or an eigenvalue problem. But that's something that I think that would make most people just quit.
Yeah.
Then you have to do determinants, and you have to all kinds of stuff.
Stop.
just gonna say no. Okay. Let's try to put this in perspective by looking at an exercise. So I don't know if any of your parents ever did this. This was in the textbook. I've never experienced this, but sure. So you have a person who rigs up a tightrope in their backyard so that their children can practice their balance. This sounds like some kind of odd punishment. It really does. I don't go stand on the tightrope. So the tightrope is placed 0.6 meters above the ground because, well, if they fall, you don't want them to get hurt badly. The tightrope is 6 meters long. And when the kid stands at the middle of it, it sags by 0.12 meters. So it's gonna go down in the center, 0.12 meters, and the child's weight is 250 newtons. Well, I'm not sure how old this kid is, but that's about 56 pounds.
Alright.
Yeah, and so this is a young kid who's like, go stand on the tightrope.
Oh, I'm gonna do that.
Okay, so let's think about what this system looks like. Just gonna draw 2 walls. Okay, then I'm going to go ahead and represent the tightrope as sagging in the middle. Okay, so we imagine that the person is on it. I don't think that that's exactly in the middle. Well, we're going to pretend that that's the middle and everything's going to line up. It probably won't, but we're going to pretend. Okay, now, the first thing we have is at this point where it's sagging, we're going to have the weight of the child. Both of those are going to be the same tension. Why? How do you know that? Not necessarily the center. How can you make it easier? Because we're going to do this again with pulleys. How do you know that this has to be the same tension? You're getting close.
Because it's level, isn't it?
Well, no, because it's the same what? Same cable.
Oh.
So yes, when it's the exact same cable, you're going to have the same tension throughout.
Oh, yeah.
Now, being in the center, we also know it's going to be the same tension because we're going to get the exact same angle of depression. Okay, so what we want to remember is essentially when that sags, we form 2 triangles, okay? The entire rope is, the entire cable is 6 meters. And so then what we're looking at, an angle theta, and angle theta, okay? Now let's think about a free body diagram for this. Man, this chapter is taking way too long. Well, I mean, I can speed things up.
No,
I
no,
can't. It's already going too fast.
Okay, so here's the deal. Like I had a tentative schedule on the syllabus of what I would like to get through. We're gonna push as hard as we can. But if we don't get through all of it, then that's just the way it is. We're gonna leave you in a place where you're gonna be able to then analyze the rest of it on your own if you have to study for, because you're gonna have the techniques to do it. If you have to study for a standardized exam. So let's look at a free body diagram for this, okay? I'm gonna draw my center point. My Y direction. And let's see. The weight of the child. Tension. Tension. Okay. can draw an X direction. And we have theta and theta. Now, how do I find theta?
You have your X, you have your X and Y components.
I just go all out.
Okay, so okay, let's look at these triangles. What trig function relates X and Y? Tangent. How do I know what my X and Y are?
They gave you.
Okay, so the entire cable is 6 feet long, child stands in the middle. How long is each?
Your X's
So
are
3.
3 meters apiece. What about the Y section of that triangle?
Oh, the point
Point
0.12.
I couldn't.
So when we say, well, tangent, I'm going to connect my X and my Y. Now let's see. Y over X. Over theta, it's going to be the inverse tangent. X. 0.12 over 3. And so theta is going to end up equaling 2.29 degrees. Okay. So this is the angle we're going to have to use to figure out our components. Okay, let's look at what our components might be. That's not X.
I thought you wrote 30.
So that's going to be the TY component for both of these tension vectors. You're going to have a TX going that way. TX going that way. And so we can start analyzing this. All right, well, let's look at Gamma forces an X. TX plus TX, but what happens is one of them goes in the positive I hat, one of them goes in the negative I hat. They're the exact same size. So you're going to have TX for the positive I hat direction minus TX for the negative I hat direction. So your X components are not contributing to this system.
Thank God. I'm not.
I'm the TX right now.
Well, you're not contributing to the system. That's awesome. Okay. What about, so essentially what we're doing is we're solving for the tension in the wire. Yeah, magnitude of the tension, because we want to solve for T. All right, so let's look at our Y direction. So what do we have? We have one of the TYs, the second TY. And yes, and this is where it can get a little confusing. You have to use both of the TY directions. Just because they both lie on that same axis doesn't mean they're a single tension. You're getting a tension from both sides.
Is the tension ever going towards the end?
The tension for what?
Will the tension ever be going towards, or like, not the tension, the. Never mind, that's a dumb question.
Okay, so look at these. Which one of these are positive based off their J hat component? Which one is negative based off its J hat component? The gravity is negative. Because the gravity, the weight, pointing down. So you're going to have Ty plus Ty minus gravitational force equals 0. Okay, well, what is Ty? So let's do the component first, because the whole thing is we're solving for that. We're solving for t. So ty going to be t sine or cosine?
Sorry.
Sine of theta. Because look at each of them. Your angle is opposite your ty. So that's going to be your sine function. So, and yes, we have 2ty equals the gravitational force.
You know, I started figuring it out.
That's
but
2t sine of theta equals the gravitational force. Your t is going to be your gravitational force divided by 2 sine of theta. And now if you were doing this as an assignment, once you get here, you're ready to plug numbers in. So what were the numbers from the problem?
250 newtons for.
So 250 newtons for the gravitational force. 2 sine of what?
2.29.
2.29 degrees. That's going to equal the tension in the cable is going to be 3128 newtons. Yeah, I thought we would get this done today, but we still have more to do. So on Friday, I would really suggest going back over tension because this is really your first foray into how forces can be multidimensional. For example, the tension can go one way or the other way, the exact same tension, just based off what part of the diagram you're referencing. And then remember, the whole point of this is find your triangles. On your free body diagram, find your triangles. Okay, so what we're going to do next time, we're going to start off with a group exercise. You're going to solve one kind of like this. I know. Except the one you're going to solve has T1 and T2, and they're both at different angles.
Okay.
Looks like these three.
It's gonna be on the quiz tomorrow.
There's not a quiz tomorrow. Nope, there's one next week and then a test the week after.
Right. I'm gonna tell my boss.
I don't hate it. I don't